All right. Well, it is 9 o'clock, and this is our first Stormwater Awareness Week workshop of the week. And this is going to be an amazing week. My name's John Tarauskas. I'm going to be one of your hosts throughout the week. And we are so excited to have each of you part of this. In fact, this year we have already well over 2,200 registrations. More than 700 unique individuals participating in this week. We have 26 different states represented, folks from 26 different states. This used to be a California event, but we have people like Phil from all over the United States now, and even 4 countries are participating in that. I think some of those are on this Zoom workshop. So welcome. If, as I mentioned previously, if you have any questions for Phil during his talk, the best way to communicate those questions would be through your chat function on your Zoom. So if you go down to the bottom of your screen, or sometimes it's at the top of the screen, there should be a chat. Go ahead and direct those questions to everyone. There's an option you can toggle who to send the questions to. Send it to everyone so that we see them as we're sorting through the questions. If we feel it's real relevant, we might even pose it to Phil right then and there. Otherwise, we'll hold it towards the end. And we're going to try to save Phil a few moments to do some Q&A with you all. So I want to introduce Phil and then give him as much time as possible for this fascinating topic of PFAS management. So Phil Farina got his education in New Jersey, where he earned a BS degree in biology and a BA in psychology. And he got an MS in virology from Rutgers University, and then he completed an MBA in chemical marketing at Farley Dickinson University. So lots of degrees, lots of education behind his topic today. And he constantly strives to remain on top with these new technologies and developments so that they can be employed in water treatment operations. So Phil currently holds the position of Midwest Business Development Manager for Clear Creek Systems, and it's a full-service water treatment solution provider. And for the past 35 years, he has been focused on development of water treatment technologies and solutions for CCRs, for remediation, for PFAS markets. And he has been instrumental in bringing new solutions to the water treatment market. So I want to welcome you, Phil, and take it away, Phil.
Thank you, John. And I'd like to welcome everyone to these opening remarks for Stormwater Awareness Week. I'm talking to you today from National Harbor, Maryland, where I am on stage at the StormCon event here for this week. So apparently stormwater this week is an extremely important topic. What we're going to be talking about today is directed towards more of a primer for PFAS remediation concepts and technologies. We're going to be talking a little bit about the new applications that are in the market. We're going to be going a lot over the how things are developing, an introduction of Clear Creek. Where do we find PFAS contamination? How should we approach it? What is the methodologies that you on the other side of this screen who are working with PFAS problems, how should you approach a solution? What are those solutions? What are some of the current PFAS treatments and technologies? And how does working with a technology-driven company like a Clear Creek to help you get to where you're going to at the end? So we're going to have a lot of information, and I'm going to try to do it as directly and rapidly as possible. But this presentation will be available online, as well as if anybody needs to reach out to me directly at any time, I'll be more than happy to work with them. So a little commercial about Clear Creek, if you'd allow me that 2 minutes of time. We've been founded in 1994. It's a family-owned business started by Tim Gannon and is now run by his son, Joe Gannon. 60 plus employees. We're constantly adding to our technical team. We are nationwide in capabilities. So we have facilities on the West Coast. We have my organization in Toledo. We have a new organization in Denver, and we're building an organization on the East Coast out of Virginia and Philadelphia. We are a full service technology solutions provider. We don't make resin, we don't make carbon, we don't make organoclay. We use all of those technologies. So being technology agnostic allows us to provide the specific technology solution for your specific problem. So we're not trying to do round hole, square peg technology. We look at your specific needs. Large scale, small scale projects, whether it's long-term, short-term remediation, permanent, all of those projects are within our bailiwick. We can design a system, build it, install it, operate it. You can buy it, you can rent it. Whatever is necessary to reach the end goal, that's how we approach the problem. Our goal is to develop a strategic partnership to provide engineered solutions to solve the most complex water treatment issues. That is how we focus our day. Some of the markets that we serve are the groundwater remediation, construction dewatering, landfill leachate particularly is becoming more and more problematic. There's a lot of bad things in landfill leachate water. All the dredging support, solid separations. CCR stands for coal combustion residual ponds that are found predominantly at the coal burning power plants. All of these need to be closed. There's a significant amount of water treatment issues associated with that. And of course, our favorite, PFAS remediation. Our corporate experience is in suspended solids management, PCBs, oils and greases, all of the metals, various and sundry methodologies of metals removal. We have extensive experience in chemical additions, whether it's for pH, flocculants, coagulants, all of the chemical addition packages. We have all of the passive and active media filters, and we utilize all of this experience in managing the PFAS problem. So that's our commercial discussion. Let's talk about polyfluorinated alkyl substances, better known as PFAS or PFOA or PFOS, or any one of 6,000 different acronyms that are used for it. We hear and see this sentence all the time. This is the forever chemical. And it is true. PFAS does not break down in the environment. But just because it's the forever chemical doesn't mean it has to be the forever problem. So let's find a way to solve it. First of all, we need to know where it comes from. You find PFAS basically everywhere. Airports are predominantly one of the more viable contributors to PFAS problems because of the AFFF, aqueous firefighting foam, that was used to protect airports from fires at airplanes. So there's a lot of testing that was done, a lot of training that was done. A significant amount of airports, whether it's commercial, military, private, sprayed a lot of PFAS on the ground and into the environment. A lot of industrial sites, anybody who was involved in water protection, shoes, clothing, wood, all of them that used a material to prevent something from being contaminated by water, they used a lot of these fluorinated substances. It got into the well waters. It got into the landfills. When you throw something away, you throw a pair of shoes away, waterproof shoes, construction debris. It gets into the landfills, the transfer stations, any recovery facilities, leachate treatment plants, the POTWs, paper. The list goes on and on and on. But it's even in rain. PFAS is highly water soluble, which is one of the means that it is used in the AFFF. So you can get PFAS in rain. So essentially, everywhere you look, you can potentially find the material. So what is a holistic approach? A holistic approach is basically the development of what you should do before you do it. And I can tell you that one of the important aspects of understanding PFAS remediation is there's a lot of things you need to do and understand before you make a decision on what you are going to do, what treatment application you're going to employ, because all of these aspects of your specific requirement will have a direct bearing on what is the treatment system that you're going to employ. So let's look at this from a holistic approach. First thing you should do is consider the water source and what you are using it for. Is it groundwater or well water? Is it pond water? Is it a subsurface bloom? Is it a municipal treatment system for drinking water? Is it an industrial waste, landfill, stormwater? All of these applications have a different solution methodology. What is the water going to be used for? Is it a drinking water application? Is it going to be released through a NIPDES permit? Is it going to a river? Is it going to another wastewater treatment system, a POTW? Are you using it for irrigation? Again, this will determine the treatment levels that you may need to apply. Different treatment levels can be accomplished through different technologies. How are you going to deliver the water to the system? Is it through a direct treatment system? Is it coming from a pond? Is it coming directly from the ground? What pre-treatments are you going to need at that point in time? Again, knowing how that water is coming to the system will have an impact on the treatment methodology. And then we also have to deal with that ugly thing of the waste streams that are associated with the treatment technology. If you use a media to take the PFAS out of your water, that PFAS is now in the media. What do we do with that media? First step, after you've defined your problem, it is of critical need to analyze the water. Now, what I always tell people is spending a few dollars on analytical today could save you tens of thousands of dollars tomorrow. So don't skimp on the analytical. It should be at a minimum. TSS, pH, PFAS, speciation is very important, and we'll talk about that a little bit later. Are there any other metals in the water? Are there organics in the water which could interfere with PFAS treatment? Are there VOCs? What other co-contaminants that are in there? The more complete that water analytical, the more successful your treatment is going to be. Once we have that, we want to understand the treatment requirements. Several states have defined hard limits. Other states have not. The federal government under the US EPA is currently promulgating the drinking water application as less than 2 ppt, but there is legislation that may bring that down to 4 parts per quintillion, which is almost to the point of impossibility of detection. But some of my colleagues in the analytical world are developing technologies to get us down to that 4 parts per quintillion. So it's important to understand what your target is. And then we also have to look at these other contaminants of concern. Just because we take the PFAS out of the water, we can't send highly dirty water that may have a high pH or metals or organics. We have to deal with all of these problems within the water system. And then finally, you need to look at, is this a permanent system, a temporary system? What's the flow rate? The flow rate has an extreme application as to the size of the equipment that you're going to need. And are we going to use a regeneratable media or are we going to use a replaceable media? We'll talk about all of these things. So, pre-treatment. One of the most important aspects of any media that's going to be used for PFAS remediation is it's expensive. One of the things that we want to make sure that we're doing is protecting that media. So we should look at the water quality and determine filtration requirements, whether it's bag or cartridge or sand or multimedia. These things are extremely important. Just going directly into a PFAS media could shorten the life of that media, incredibly increasing the cost of your treatment. Oil, you should look at oil and water separators or other methodologies to remove oil from water, because these have an extremely negative impact on most of the medias. And do we need coagulation, filtration, settling to enhance the filtration process? All of these things will be determined through the water treatment or the water analysis that we just discussed. We have to then look at some of the chemicals that may be employed, polymers, flocculants, coagulants, pH adjustments. All of these need to be considered before we start to do anything. Then we get into the treatment portion of the media. And we're going to discuss each of these medias in line. There's carbon media, which is GAC, granular activated carbon. We have organoclays, which are naturally occurring substances that have a surface modification that has been designed specifically for PFAS remediation. We have the designer material, the ion exchange resins. These are man-made resins that are designed specifically for PFAS remediation. And then there are blends. We can blend carbon with organoclay. We can use organoclay in conjunction with ion exchange. These things are very important, but in order to understand which one or ones to use, that analytical becomes critical. We talked about metals. Metals can be removed from water either through settling, filtration, coagulation, but we also can remove them through ion exchange resins, zero valent iron media, activated alumina, reverse osmosis, and other forms of technology. So again, if you have metals in your water, you can remove those as well. So it is a total process that you need to look at. Let's get into some of the medias that we talked about. Carbon, also called granular activated carbon. Very well-known material, significant history, lots of data on applications. It is more used for general applications. Now, you can use it for specific applications like drinking water, but you will find during the course of this presentation that it may not be sufficient alone for a drinking water application, but can be used in conjunction with either an organoclay or an ion exchange resin. You will hear often virgin or reactivated carbon. One of the things to think about, if you reactivate carbon, that's a process that employs heat. When you heat carbon, you change the surface nature of that material as it gives off the PFAS as part of the regeneration process. This reduces the carbon's ability to work in the future. So reactivated carbon has a life cycle of about 80% of virgin carbon. So when you're looking at a new application that is going to be a long-term application, or an application where you're trying to get to very low levels of PFAS in your treated water, stick with the virgin material. It likes the mid-range and longer chain molecules. It's not so great on the short chain. It's not so great on the branch chains. So going back to that speciation, by knowing the species that are involved, we can determine which of the medias would be applicable. Let's talk about organoclay. It could be used alone or in conjunction with other materials. These are surface modified bentonite, naturally occurring clays. Very strong proven results. And this is a renewable resource, much like carbon. It is a mined material, easily found. Ion exchange resins, this is the newer technology. It is a proven technology that can be used with or in conjunction with carbon. They're man-made polymers specifically designed for specific PFAS. Again, knowing the speciation helps you determine which resins to use. This likes the long and the short chain materials. Again, knowing the speciation helps us determine which materials. Let's dig into the medias themselves. Carbon. Low cost in general for a pound of material, but because of the amount of material that you may need, because of the size of the equipment necessary, And because of the life expectancy of carbon, it may not be the lowest cost of ownership over the period of your project. If you have a short-term project, certainly carbon would be something that can be used. Much longer-term projects, you have to consider the cost of change-outs and disposal of the media. Very easy to obtain, multiple packages available, easy disposal either through incineration or landfill, or it can be regenerated. Very, very good for short-term projects, and it has a high flow capability. So you can use it at 500 gallon a minute, 1,000 gallon a minute. It's just that you break it down into different trains. Some of the negatives, as I said, it exhausts quickly, possible frequent changeouts. We talked about knowing what your target application is. Very difficult to get below 7 ppt on a consistent basis. Getting to that 2 ppt, it's more difficult. It can be easily clogged, which is why you have to protect the resin up front. It allows some PFAS to pass through. It also gives up some PFAS as it reaches levels where it begins to get exhausted. It will preferentially give up a shorter chain for a medium chain. Regenerated is only 80% as effective. You have to use virgin only in drinking water applications, and total cost of ownership may be higher when you evaluate the total project costs. Granular activated carbon comes in 2 forms, bituminous or coconut. Bituminous is preferred for PFAS remediation. It is a much higher capacity and a much faster application material. You do require larger vessels because you have to have a 20-minute empty bed contact time. You will always have a lead lag vessel configuration. This is important when you're dealing with limited floor space. It does remove a lot of the other organics that are in there. So if you have a high organic load in your water, we may use granulated activated carbon focused on the organics and then something else focused on the PFAS, because organics will interfere with PFAS uptake. It has an absorption methodology so that it has a quick grab, but it also allows some of that to desorb and go back into the stream. Organics will impact the PFAS take-up because they compete with it. The other parts are preferences are given to the long and mid-range molecules. It does like the branched molecules better than linear. It has the hydrophobic materials or have a much stronger affinity, and it could exhaust quickly. One of the things I want you to remember on this slide is that use of 30,000 bed volumes. That's an anticipated concept of the exhaustion level. So after about 30,000 bed volumes, you have to start considering to replace that material. Hold on to that number because we're going to compare that number to organoclay and to resins.
And Phil, we have a question that I think might be appropriate. Someone asked, is incineration an acceptable method for disposing of media that's been impacted with PFAS?
With the exception of the Department of Defense, which has recently issued a moratorium on the utilization of incineration, the answer is yes. You can effectively use incineration. There are 4 approved incinerators in the United States that have all of the necessary vapor recovery and all of those things with it. Remember, if we take PFAS out of water, it goes into the media. We have to deal with that media. There's only 2 options, incineration or landfilling. If we landfill it, there are a number of approved specified landfills for long-term holding of PFAS-laden media. Right now, there isn't a third option. There's no biological treatment. There's no other effective economic methodology. So landfill right now is the predominant methodology, but depending on your location and your feeling for incineration, with the exception of the DoD, incineration is a viable solution for these medias. Does that answer your question, I hope? This is a typical GAC system. We have our filtration system up front to protect the media, and then a lead lag system of two vessels. Now, organoclays. Organoclays are either a bentonite or a zeolite clay material. Predominantly, the ones that seem to be working better are the zeolite types of materials. These are naturally occurring, they're mined materials, but as a clay, the surface needs to be modified with a surfactant material to allow the PFAS to come in contact with the clay material and to adsorb or absorb into that clay material. It really likes the PFOA, PFOS, also called AFFF. All of the other fancy ones, the FTCA, the FTSA, all of these different types of sophisticated PFAS materials, organoclays are the way to go. Long and short chain species, particularly, it does a really nice job on the branched species, and it has a much, much higher working capacity, which means it can pull out a significantly greater amount of material before exhaustion. And we'll talk about that on the next slide. It works in two methodologies, from an ion exchange mechanism and an adsorption mechanism. And you can absolutely reach non-detect levels. Again, in this particular time, non-detect is a level below 2 ppt. Negatives, it is a hydrophilic surface, so it has to be pre-treated. It is now pre-treated by the manufacturers. So it has eliminated all of that pre-treatment that was done on site. So although this is still a negative, it is now moved over to an insignificant. And again, much like all of the other medias, pre-filtration is absolutely necessary to protect the media and keep it from clogging. Recently, organoclays have been approved in drinking water applications. So we are now seeing a lot of the large municipal treatment facilities are moving towards organoclays and IX resins, and they're moving away from carbon. It can be used in conjunction with carbon. Carbon can be used in front of an organoclay to improve flavor, remove odor, improve taste, take out organics and that area, and then use the organoclay as a polishing step. Depending on the quality of the water, we can also use organoclay alone. It is a lead lag configuration, so we still need 2 vessels at a minimum, and that obviously is dependent upon the flow volume, determines the size of the vessels. You can blend it with carbon in the same vessel, so you can reduce your footprint by having an organoclay carbon blend, and that's where we would work with you to determine how that can be done. If you're doing organoclays, it will pull oils out of the water. So sometimes we see organoclays in front of carbon, but those organoclays are not the same that we would use for PFAS. Those are another class of organoclay that is designed to remove the oils, and we call that a sacrificial organoclay because it's really not working on PFAS. It's really working on pre-treatments to improve the water quality before it gets to the media. A higher holding capacity before exhaustion. Remember, we talked about carbon as 20 minutes empty bed contact time. Now we're at 5 minutes empty bed contact time. This really shrinks down the size of the equipment that we need at higher flows. We had carbon at 30,000 bed volumes. This is 50,000 bed volumes at a minimum. We have seen some performance numbers that are in excess of 350,000 bed volumes. Typically, this means we're talking about materials that would last upwards of a year, as opposed to materials that will last 3, 4, 5, 6 months, like in a carbon application. A typical organoclay GAC system, we can go with organoclay up front And what we're showing here is the volume of organoclay that's necessary is smaller. So that's signified by a smaller vessel. And then we can have GAC as a polishing afterward to remove odor, color, taste, etc. Or we can reverse that depending on the quality of the water, where we might be using the GAC up front to take out some of the pre-treatment materials, and then use the organoclay after the GAC as the polishing step. So again, determining what your water quality is determines the media that you're going to use, determines the course of treatment from pre-treatment all the way through media selection and linearity of what media is going to go first. Ion exchange resins. A lot of companies make ion exchange resins. They are somewhat in short supply, predominantly because very little ion exchange resin is made in the United States, mostly made in Asia, Europe, South America. So there's a lot of importing of these materials, but they are specifically made for PFAS removal. These surface modified materials can be modified for the specific PFAS that you're looking at. So again, it's important in the early stage to have done that speciation so that we can help choose the right ion exchange material. This works by, as it says, an ion exchange mechanism, but there's also adsorption. The PFAS will go into the resin body itself and be removed both by ion exchange and adsorption mechanisms. Wide variety of resins available from a wide number of producers. Very, very high holding capacity. This material can hold a significant amount of PFAS before it reaches exhaustion. Easily reach non-detect levels. It's a consistent material for the water treatment applications for drinking water. It is a material that can be counted on to stay at those very, very low levels. Because it has a very high holding capacity, allows for less frequent media change out. So that this media, although it may cost significantly more per pound up front, when you look at the entire cost of ownership, it becomes very competitive to the pricing of a carbon or an organoclay. Some resins can be regenerated. Now, some resin manufacturers are taking resins back to a regeneration facility. That seems to be preferable than doing regeneration on site. Regeneration on site is a very complicated methodology. It requires the use of a methanol solution. This then requires explosion-proof and fire-proof and spark-proof buildings, etc. So when you're dealing with regeneration of resins, it is usually done back at the resin manufacturer. One of the new and exciting things we talked about, incineration disposal. Exhausted resin has recently been approved as a fuel in cement manufacture. So if you're aware of the manufacture of cement, they use a rotary kiln at temperatures in excess of 3,700 to 5,000 degrees centigrade. You can use this exhausted resin as part of that fuel that's used in the manufacture of cement. And at those temperatures, it completely destroys the material. There's 4 approved rotary kilns in the United States that can accept ion exchange media as a fuel. So we're working to find methodologies for disposal of this material. From a negative standpoint, inorganics really impact the performance. Again, by doing the analytical, we know what inorganics to deal with. We can treat up front. We can improve the capacity of the resin to work. Limited availability, sometimes we're seeing several months before material may be available for certain applications. So we have to plan in advance. So I know a lot of people like to wait till the last minute to make a decision to, okay, it's time, we're going to go ahead and do it. we're going to order the material on Tuesday, we'll have it here on Wednesday. That's not going to happen. It's going to be 30 Wednesdays down the road before that material becomes available. So if you have a timeline, please try to work in advance of your timeline, because it's very important that we don't want to exceed a timeline where problems exist in areas where you might see fines or having to shut down a well because it is not treated in time. We talk about some of the contaminants, SO4, nitrates, sulfates, hydrocarbons, HCO3, chlorine. All of these things need to be dealt with because they impact the performance of ion exchange resins. And like every other resin, TSS, organic matter, is going to foul that material. So again, like any other media, you have to remove those materials up front. So that's where pretreatment comes into play. A little bit deeper, we talked about filtration. You should know the species of the material that you're going to be treating to allow for proper selection of the resins. These resins prefer the acidics, so the PFOS and longer chain species, but it is excellent for AFFF, which is, again, the predominant species that we see. But well waters and remediation waters, river waters, pond waters, all respond very, very well to ion exchange resins. They do have some affinity for the shorter chains, but they do like the longer and branch chains better. Two mechanisms, we talked about that before, ion exchange and adsorption. So you have this rapid rate of response. It can be used alone or in conjunction with carbon. Again, as always, the lead lag configuration, very high holding capacity, very quick reaction time. So 20 minutes empty bed contact time for carbon, 5 minutes empty bed contact time for organoclay, 2.5 minutes for resins. This allows us to bring those vessel sizes down substantially. One of the really great things about resins, depending on the quality of the water and how it is managed, some of these resins may last 1 year to 3 years before you have to change them out. So knowing the speciation up front, knowing the quality of the treatment, knowing the amount of PFAS that's in the water, we can utilize that information in working with the manufacturer to determine the life cycle of that material. We talked about 30,000 bed volumes for carbon, 50,000 bed volumes for organoclay. Here we're looking at 100,000 bed volumes for ion exchange resin. And there is some cases where we've seen as much as 750,000 bed volumes. Very long life cycles of these types of materials. A typical system might be your pre-filtration system up front. We could use GAC or not use GAC, depending on the quality of the water. But if there's organics or some of these other things that are in there, we want to protect the resin. And then again, we need a smaller volume of the resin. So that's signified by having the smaller vessels there. So a very linear type of progression for treatment on all of these things. Not a lot of steps, not a lot of things going on, very limited manpower requirements, not a lot of high technology, don't need a great deal of PLCs. So it is a straightforward contact type of a system. Other technologies that are up and coming, but have not really reached the level of high level installations. Nanofiltration can be used in combination with media. It's a point of view system in homes. So if you're dealing with a home and you have these under the sink filtration systems or these whole house filtration systems, they frequently employ the nanofiltration type of technology. Up and coming is electrocoagulation. In this case, what we're doing is cleaving the fluorine bond. And when you break that fluorine bond off, you create fluoride. Well, fluoride is the safest form of fluorine. The problem, unfortunately, is that the fluorine-chlorine bond, I'm sorry, fluorine-carbon bond is very, very strong. So it takes a significant amount of energy to break that bond. So in electrocoagulation processes, it may require large systems, a lot of energy in order to impact that PFAS molecule. Electrocoagulation is being studied by a number of vendors. It may be something in the future, but again, it's for low volume, smaller volume types of applications. Chemical destruction of the fluorine bond has been under discussion for a long time now. University at Pittsburgh, University in Cleveland, University in Philadelphia, all have ongoing chemical destruction technologies. They've done work with it. They're in the very small volume stages. It is still well within the research stage. RO membranes, reverse osmosis membrane systems, can be employed, have been employed, particularly in the drinking water world. This produces a very, very clean water. However, the PFAS molecule builds up on what we'll call the brine side of the membrane. So now we're dealing with a fluid material that could be 5 to 10 times more concentrated than we started with. So we now have to deal with a methodology of disposing anywhere between 10, 15, as much as 20% of the water volume with a very high concentrated PFAS brine water. You do have a shortened life cycle on some of these membranes. So you may have to change the membranes out more frequently, depending on the quality of your water and the type of PFAS involved and the flow volume. And you can use a 1-stage or a 2-stage. You can have a high pressure system, a low pressure system. So there's a lot around the RO membrane. In some cases, it may be the right way to go, but in a lot of other cases, media technology is the workhorse. If you want to include an RO, you would include that as a final polishing step after all of the media applications are concerned. Biological treatment is kind of my favorite as a virologist by training. I've spent a lot of time in the biolabs. Biology does not like the fluoride-fluorine bond. It is a man-made material. It's not naturally occurring. Biology has not caught up yet to chewing up man-made materials. There are some designer microbes that are being created that have some affinity for the fluorine carbon bond. However, my opinion as a virologist, I don't like making new bugs and releasing it into the environment. We don't know what they're going to be like down the road. We don't know what impacts they're going to have in the environment as they begin to grow and multiply. And because they're a living creature, they will change in species. They will become something different. We just don't know what that is going to be as time goes on. So we are still looking for that magic bug. So in conclusion, the holistic approach basically involves 3 areas of concentration. Understand the water. Do as much as you can on the water chemistry. Understand your stream. Understand your source water. Understand your permit requirements. Understand what your target is. Second step is define the specific outcome: long-term, short-term, drinking water, NIPD's permit, wastewater treatment facility, POTW, 7 PPT, 70 PPT, 2 PPT, 4 parts per quadrillion. Know all of that before you start to build that system. Once we work collaboratively on steps 1 and step 2, we can then design that specific treatment system, get something that is designed for your flow rate, for your water treatment, for your inbound water, and define that for your final treated outcome water. So in conclusion, Clear Creek Systems wants to be your partner in PFAS remediation management from start to finish. We will walk you through all of the things that you need to do and try to help you understand all of the steps from beginning to end. So how do we do that? We do that through individually engineered solutions for all PFAS applications. So everything we do is customized, fabricated. They can be self-contained systems. They can be systems like we saw in the picture behind me. They can be permanent. They can be temporary. They can be rented. They can be purchased. Anything that you need to make it happen for your system, we can put that together. We can also supply all of the field services, installation, operations, maintenance, upgradability, optimization, evaluation, all of the steps that are necessary to manage a purchased system or a rental system. And I will conclude with my contact information. I would ask you, please, if there is any interest in having us work with you to help define your situation and help meet your requirements, you can please call me directly. I am the PFAS manager or subject matter expert for Clear Creek, but I have a team of people all throughout the United States that are local for each individual organization that can handle any questions, any installations from Maine to Florida, from Washington State to Southern California, and all parts in between. I know that was a lot of information. I know that was relatively rapid, but it gives you an idea of what you should be thinking about and some of the concepts that are available for treatment technology today. I thank you for this opportunity. And John, I turn it back to you, sir.
Well, thank you, Phil. Why don't we open this up to some questions? And so if you have questions, you can enter it into the chat. Or if you prefer, you can unmute yourself and ask Phil a question. Phil, why don't I kick it off with one that gets asked? I'm sure you get this asked almost every week. Okay, how much does it cost? Are there any studies or figures at a, per million gallons or per quantity as far as cost?
A typical drinking water application, okay? If you are a municipality or a small well municipality or something where you're already treating the water up front, so you're taking out, you're doing some solids work, you're doing some odor control work, you're doing some taste and some of these other things, and the PFAS has not been managed, okay? So what we're going to add is a PFAS system, whether it's more carbon or resin or ion exchange. A typical number for that is approximately 0.00014 cents per gallon on an annualized basis. Your first year, you're going to have to put in equipment. So there's going to be some equipment costs. In your first year, you're going to have to put in resin. So there's going to be an additional capital cost with the equipment cost. Your operational cost in your first year, if you're using a resin or using a organoclay, is lower. So it's the second and third year. So it's not like it's $1 million and then it's okay up, for the next 2 or 3 years. So it's approximately 0.00014 cents per gallon over the lifetime of a media.
Okay. All right. Good. And we got a question asked, is this presentation available to us? And yes, it is. In fact, if you go to the Stormwater Awareness Week website where you registered for this event, go to the menu, look for resources, And then there'll be another link to where you could download the presentations. And Phil has included several resources, including this presentation that you can download as a PDF. Plus this recording of this workshop will stay online indefinitely, so you'll be able to use that as well.
And if anyone would like to have a live presentation designed specifically for them, I know there's possibly some environmental engineers or consulting engineers that might be involved in this discussion today. If you would like to have a presentation designed for your specific group and have Clear Creek come either do it as a flat screen or do it as a lunch and learn so that we can have a conversation, we are available. I am available for that anytime.
Okay, anybody else have any questions? If you do, go ahead and unmute yourself. We have just a few more minutes. And of course, you have Phil's contact information. Oh, can you speak on applications for stormwater management? This, after all, is Stormwater Awareness Week. Have they even started that yet, Phil? And what's your thoughts?
On the West Coast is kind of a leader in PFAS management for stormwater applications. And we do a lot of stormwater work on the West Coast. And, you know, you predominantly begin with capturing the water, doing some filtration, doing some metals removal, perhaps, depending on what's happening, certainly TSS and pH. That system, you can simply add 2 vessels, depending on your volume, whether they're larger vessels or smaller vessels. Like, you know, behind you, that's a stormwater type of a setup where we have carbon taking out some of the organics and some of the colors and some of these other things that might be in the water. And then you can have some resin systems behind that. So this is easily buttoned on to the back of a stormwater system, and it doesn't add a tremendous level of complexity. So very easy to button onto a stormwater system. Okay.
How about, we have another question. How is this applicable to the treatment of processed wastewater?
Same thing. The media is stupid. It doesn't know the source of the water. It doesn't know what it's trying. All it knows is there's something coming in, there's a chemical or physical attraction that takes place, and water goes out. So all of the same things we talked about on the pre-understanding of the water, those are still important to industrial applications. You know, landfill leachate water, if you have to know what's in that water in order to treat it so that you don't destroy your media. So any water source, you can take this same step-by-step methodology and get to the same end zone. I know it costs $1 to run the analytical, but I'm telling you that dollar spent can save $10 down the road.
All right, thank you. All right, Bill, this has been a great way to kick off Stormwater Awareness Week. Awesome workshop. I know people are going to have questions. Here's another one that just came in. Do you guys have pilot or bench scale studies that you've done or are making available literature on any bench studies?
We have done bench scale studies. We have pilots that are in a Connex box that we can test organoclay, carbon, resin, combinations thereof, pretreatments. So I mean, we can bring a pilot study to someone's facility. All of the resin manufacturers have pilot study work. All of the organoclay manufacturers have pilot studies work. But you know what? This goes back to that round peg, square hole scenario. A system that was developed for someone else may not work for you because your water has this in it as opposed to that in it. So yes, I can give you that data. Yes, we have that information, but it is really a highly specified treatment system that gets you to where you're going.
Right. Aziz, I have a quick question. I asked that question about the pilot study. Do you guys provide services to do pilot studies like
Absolutely.
At the plant? Okay.
All the time. And yes, absolutely. contact me at your leisure and I will set you up with the right people. But yes, we can do a pilot study immediately.
That's good. Thank you.
You bet.
All right. Well, again, thank you for joining us for Stormwater Awareness Week. We have a lot of workshops left. This was only our first one of the week. There's another 28 or so, plus our 3 keynote sessions or their recorded videos that you won't want to miss. So check it out. Go to stormwaterawareness.org. You still can sign up for any of the workshops. I will tell you, though, the one at 11 o'clock with State Water Board's Brandon Rosenboom has sold out. We actually reached our Zoom capacity on that one. So you can watch that recorded probably within a few hours after it happens. But join us for the future, for the next workshops, and I'm sure we'll see you in another one. So thank you, Phil, for joining us. And thank you to each of you.
Thank you very much for the opportunity. And if anyone would like to have any further deeper discussion, we're here to help all the time.
All right.
Thanks, everyone.